Let's evaluate the double integral of the region for the function of x and y for the differential area, where f of xy equals e to the negative x squared plus y squared over 2, and R is the region defined by R, which is x squared plus y squared less than or equal to 25, and x is greater than or equal to 0. Let's begin by sketching the region. And we're looking at the region where x squared plus y squared is less than or equal to 25, and x is greater than or equal to 0. So this is a circle with a radius of 5, so everything within the circle as well as everything greater than or equal to 0. And what we'll end up with there is the right half of a circle of radius 5. So again, the x squared plus y squared is less than or equal to 25. That's everything inside a circle of radius 5. And x greater than or equal to 0, that's everything to the right of the y-axis. Now we can determine our bounds of integration. We can slice it like a pie here and determine our inside radius. Our inside radius would be actually the origin, r equals 0. The outside radius would be the radius of the circle, 5. The smallest angle theta, or your lower bound for theta, would be equal to, let's say, negative pi over 2. And then the largest angle theta would equal pi over 2. So that's our region. And now we want to evaluate this function here. It's double integral. So it's going to be double integral r of f of xy. Well, f of xy is given to us over here as e to the negative x squared plus y squared over 2, and then our differential area. Now, since we're using polar conversion here, our differential area is going to be either r times d theta. So dA is equal to r times d theta. Or it could be in the order of r times d theta times dr. Since our bounds, lower and upper, for both r and theta are constants, we can actually do this in any order. So if we then continue to substitute, we know using the conversion equations that x squared plus y squared is equal to r squared. So this can be written as e to the negative r squared over 2. And our differential area can be written as r times d theta, or it can be written as r times d theta times dr. Since they're both constant bounds for r and theta, we can actually do it in any order. If we choose the order d theta dr, that's going to make the first inside integral a little bit easier because we're treating r as a constant and theta as a variable. So our bounds for theta would be the inside bounds from negative pi over 2 to positive pi over 2, and the outside bounds would be for r, which go from 0 to 5. Let's evaluate the inside integral. Since this differential is d theta, we're going to treat theta as a variable and treat r as a constant. So this is really one entire big constant here. The antiderivative of that constant would be that constant times theta. So it's going to be e to the negative r squared over 2 times r times theta, where we're going to evaluate theta from negative pi over 2 to positive pi over 2, and then our differential r. When you plug in pi over 2, and then you subtract what you get when you plug in negative pi over 2, we'll see that this is going to simplify. So it's going to be e to the negative r squared over 2 times r, and when we plug in theta equals pi over 2, minus what you get when you plug in negative pi over 2. You see this minus and then negative. You have a pi over 2 plus another pi over 2. It's like a half a pi plus another half a pi is an entire pi. So this integration, when you write it, is going to be pi times e to the r squared over 2 times r, and this is an integral, and you can bring that pi out in front, dr, where r goes from 0 to 5. Now you can use substitution here so that you can write it in the form of e to the u du. If you let u equal, sorry, that should be a negative r squared over 2, then your du needs to be negative 2r over 2, which is negative r dr. We do have the r in the dr, what we don't have is that negative, so we'll bring that negative out in front with the pi. So this integral becomes a negative pi times the integral from, actually let's wait on that bounds, so it's be negative pi times the integral of e to the u du. Now we do have our bounds for in terms of r, and we can make the substitutions here to find our bounds in terms of u. When r is equal to 0, then u is equal to 0. And I'm looking at this to make that conversion, so my lower bound is still going to be 0. When the upper bound was r equals 5, and you plug that into here, it's going to be negative 5 squared over 2, or negative 25 over 2 is going to be your upper bound. Now it's been completely written in as u substitution, so the antiderivative of e to the u du is e to the u. That's going to be negative pi times e to the u. Evaluated for u goes from 0 to negative 25 over 2. We're going to plug in the upper bound. It's going to be negative pi times the quantity of e to the negative 25 over 2 minus what you get when you plug in 0, and e to the 0 is 1. So this would be your final exact answer, or you can use a decimal approximation by taking a graphing calculator using the integration feature to evaluate it numerically.